Hello my friends and welcome back to the You Can Do TV channel. Black Rock Studio in Toronto, founded by Catherine Carroll, is renowned for its exquisite handmade tiles that embody old-world craftsmanship and meticulous attention to detail. The production process begins with selecting solid clay, which is carefully cut into custom shapes based on the client's design preferences. If the design includes textured tiles, these patterns are applied during this stage. Once shaped, the tiles undergo a drying process to prepare them for glazing. The studio produces each tile with a focus on individuality and quality, ensuring that every piece is a work of art. Hand glazing is where the unique character of black rock tiles truly emerges. Each tile is brushed with custom glazes, creating variations in hue, texture, and shading. This step ensures that no two tiles are identical, enhancing their artisanal charm. After glazing, the tiles are loaded into a kiln and fired at high temperatures for approximately 8 hours. This process not only solidifies the glaze but also ensures the tile's durability and longevity. Once cooled, the tiles are assembled onto mesh sheets for ease of installation. Egyptian cement tiles are handcrafted in a process that combines traditional artistry with practical methods. The process begins with the preparation of materials. White cement is sifted into a fine powder and mixed with pigments to create the desired color. Achieving the perfect hue requires precision, as color plays a crucial role in the tile's final appearance. Water is then added to form a smooth, workable mixture. Next, the colorful cement mixture is carefully poured into a mold using stencils. These stencils, often decades old, create intricate patterns and designs. Some artisans add details freehand, showcasing their mastery of the craft. Once the colored sections are completed, the mold is topped with a blend of sand, cement, and limestone. This layer reinforces the tile and secures the design in place. The filled mold is then placed in a hydraulic press. Intense pressure solidifies the cement within seconds, creating a durable, high-quality tile. After pressing, the tiles are left to cure, a process that enhances their strength and longevity. Despite the rise of ceramic and marble tiles, as well as the high costs of materials and labor, a few artisans remain dedicated to this traditional craft. They produce tiles not only as functional flooring but also as vibrant pieces of art. Workshops sustain this heritage by mentoring young craftsmen and adapting designs to modern tastes, ensuring that the legacy of Egyptian cement tiles endures. This craft, dating back to the 19th century, gained popularity when cement became a cost-effective and durable building material. Despite the challenges posed by modern alternatives, Skilled artisans continue to preserve this tradition in Cairo workshops. The process of making pavement tiles from plastic waste involves several key steps, focusing on recycling and repurposing materials that would otherwise pollute the environment. First, the plastic waste, which can include polyethylene film, plastic bags, toys, and car bumpers, is collected and sorted. The waste is then fed into a crusher, which reduces it to smaller particles, making it easier to process. Next, the crushed plastic is transferred into a mixer, where it is blended with a special dye if desired. The plastic mixture is then sent to an extruder, where it is heated and shaped into a consistent material. This material is then placed into a hydraulic press, where it is formed into tiles. Depending on the design, different molds are used to create either simple, flat tiles or more robust, pattern tiles that can withstand vehicle traffic. The tiles are subjected to high pressure for about 40 seconds, allowing the plastic to cool and solidify. Once cooled, the tiles are removed from the mold. The result is a durable product that is often stronger than traditional concrete tiles. These tiles can be made in various colors by adjusting the dyes used in the mixing process. The production of pavement tiles from plastic waste offers a sustainable solution to the growing issue of plastic pollution. It provides a way to recycle various types of plastic waste, turning them into useful and long-lasting products. Additionally, this process supports a circular economy, as the tiles themselves can be recycled after their lifespan, contributing to the reduction of environmental waste. The glass recycling process begins with the collection of waste glass, either from bottle bags or dry commingled collections. At the materials recovery facility, the glass is separated from other recyclables before being transferred to a dedicated glass recycling plant. In the plant, the first step is the removal of ferromagnetic impurities through magnetic separation, followed by screening to eliminate oversized, uncrushed materials. These materials are sent to a pre-sorting stage, where bulky pieces and large contaminants are manually or automatically sorted out. The glass is then crushed using a roll crusher to achieve a uniform flat particle size. Next, the glass undergoes a drying process using a rotary drum dryer and a drying air extraction system, which also cleans the surface of the glass. The material is then subjected to further separation of metallic materials, using magnets and eddy current separators for ferrous and non-ferrous metals. Optical sorting is employed to remove plastics and other inert materials using a combination of color cameras, near-infrared sensors, and X-ray fluorescence technology. These sensors detect lead glass and glass ceramics. Finally, the glass is color sorted, ensuring a purity of up to 99%, with materials like flint, amber, and green glass being separated. The finished cullet is ready for reuse in glass container production, completing the recycling cycle. In an effort to reduce the environmental impact of concrete production, innovative methods are being explored, such as using recycled glass as a sand replacement in concrete mixes. This initiative aims to address the scarcity of natural sand, which is commonly used in construction but is being consumed at unsustainable rates. In collaboration with research and industry partners, the Metro Tunnel Project has adopted the use of crushed glass in the construction of temporary blinding works at the State Library Station site. The process begins with the collection of curbside waste glass, which is then processed at a recycling facility, where it is broken down and further refined using extreme whirlwinds to achieve ultra-fine glass sand. This sand is screened to remove larger particles and impurities. The finely processed glass is then mixed with cement to form concrete at Wholesome's batching plant, replacing conventional sand. The concrete is tested for durability and strength, ensuring it meets the necessary standards for infrastructure projects. By incorporating recycled glass into concrete production, the project aims to reduce cement use and its associated carbon footprint, paving the way for the future commercialization of glass-based concrete. The rubber tile production industry has grown significantly in recent years, driven by increased demand for sustainable, durable, and impact-absorbing flooring solutions. Rubber tiles are widely used in gyms, playgrounds, sports facilities, commercial spaces, and industrial areas due to their safety features, slip resistance, and ease of maintenance. The industry primarily relies on recycled rubber from end-of-life tires, with approximately 1.5 billion tires discarded annually worldwide, providing a steady source of raw material. A typical rubber tile production line includes several key steps: raw material preparation, mixing, molding, curing, and surface finishing. The process begins with shredding recycled rubber into granules of 1 to 4 millimeters in size, which are then mixed with a polyurethane binder and pigments. The mixture is placed into molds, where it undergoes compression molding at pressures of around 15 to 20 megapascals and temperatures between 140 to 160 degrees Celsius. The curing time varies between 5 to 20 minutes, depending on the tile thickness and production method. Tile thickness typically ranges from 10 millimeters to 50 millimeters, with denser tiles used for industrial applications. An average medium-sized rubber tile manufacturing facility can produce 500 to 1,000 square meters of tiles per day, depending on the plant's automation level and workforce size. The industry is expected to grow at a compound annual growth rate, CAGR, of 6 to 7% from 2023 to 2030, driven by increased focus on eco-friendly building materials and stringent safety regulations in public spaces. On the cost side, raw materials account for roughly 40 to 50% of production costs, while labor and energy contribute 20 to 30% each. High-quality tiles can retail for $10-25 per square meter, depending on specifications such as thickness, design, and application. With advancements in production technologies, manufacturers are focusing on cost efficiency and enhanced product performance to remain competitive in this evolving market. Recycling plastic and glass waste into concrete paver bricks involves a systematic production process. First, waste plastics are shredded using a plastic shredder. Simultaneously, glass bottles and other glass waste are crushed into fine particles using a crusher. The shredded plastics and crushed glass are combined with ordinary sand and cement in a ratio of 1 bucket each of crushed glass, shredded plastics, sand, and half a bag of cement. This mixture is thoroughly blended using a multi-purpose mixer to ensure uniform consistency. Once mixed, the material is fed into a concrete brick molding machine to form the desired paver bricks. The resulting eco-friendly bricks are durable and sustainable, offering an innovative solution for managing plastic and glass waste. Key equipment includes shredders, crushers, mixers, and brick molders. The process of turning plastic waste into a low-carbon concrete additive involves several key steps. First, plastic waste, often deemed unusable by traditional recycling methods, is granulated and co-mingled with mineral additives, primarily calcium hydroxide and pozzolan ash. The typical composition is 80% plastic and 20% additives. This mixture is then subjected to a heat extrusion process, raising the temperature to approximately 240 degrees Celsius. The extruded material is cooled and chopped into granules matching the size gradation of sand used in asphalt or concrete. The K-brick is a groundbreaking building material that addresses key challenges in construction, including brick shortages, housing demand, and sustainability. Made from over 90% recycled construction and demolition waste, the K-brick is an unfired brick that significantly reduces carbon emissions and energy use. Unlike traditional fired bricks, which require kiln temperatures of up to 1,200 degrees Celsius and extensive fossil fuel consumption, the K-brick employs an innovative compression process, eliminating the need for firing and cement. The process begins with the collection of certified inert waste and waste plasterboard, which are blended using Canotech's proprietary method. This closed-loop system recycles materials that would otherwise go to landfill, transforming them into durable bricks suitable for construction. The resulting product is versatile, available in various colors, and aligns with European waste reduction legislation, which mandates increased recycling and minimal landfill use. Supported by the Construction Scotland Innovation Centre and Hamilton Waste and Recycling, the K-brick exemplifies sustainable innovation, offering a practical solution for eco-friendly construction while addressing global environmental and housing challenges. Brick production is a significant industry in Nepal, with over 1,000 brick kilns operating nationwide. The Kathmandu Valley alone hosts 200 brick kilns, while others are spread across various districts, particularly in the Terai region. Each kiln produces between 3 million to over 10 million bricks in a single season, depending on its size. Small and medium-scale kilns typically manufacture around 3 million bricks, whereas larger ones exceed 10 million bricks per season. The brick industry contributes approximately 4% to Nepal's GDP, underlining its importance in construction and development. The production process is heavily labor-intensive, with 60% of the workforce coming from India. Each kiln employs between 400 to 1,000 workers. However, the industry often faces challenges due to labor shortages, impacting the quality and quantity of production. Labor costs account for 80 to 90% of the total investment in brick manufacturing. To address these challenges, the adoption of machinery like the JCB telehandler has emerged as a game changer. These machines streamline operations such as brick shifting, soil handling, leveling, truck loading, hopper feeding, and coal handling. By reducing manpower requirements by up to 50 to 60%, they save up to 0.3 cents per brick, potentially cutting costs by approximately $30,000 per season for kilns producing 10 million bricks. Devi Chambers Bricks, located in Dindigul and Palani, is known for producing high-quality wire-cut, vacuum, and machine-made bricks. The production process is meticulously designed to ensure premium quality through careful selection and processing of raw materials. 3 types of soil are blended in precise ratios to create the ideal raw mix. This blend is loaded into a box feeder and passed through a series of 3 crushers, which pulverize stones in the soil to enhance the surface finish of the bricks. Water is then added to the mixture, which undergoes a 5-stage mixing process in a final mixer to achieve perfect clay consistency. The unique 5-stage mixing system was developed to enhance precision in the blend. The resulting clay is passed through a vacuum extruder that de-airs the material, increasing its density and wet strength. The extruded clay emerges in long columns, which are cut into individual bricks using advanced hydraulic cutting machines equipped with precision sensors for accuracy. Once cut, the bricks are stacked using robotic stackers onto pallets for drying. Initially, they are shade-dried before being transferred to open areas for further drying. Following this, the bricks are fired in kiln chambers at controlled temperatures for 40 to 50 hours. This critical firing step imparts the bricks with their characteristic color, density, and solidity. Proper firing ensures that the bricks produce a distinctive clay pot sound when struck, signifying their quality. Technological advancements enable the workshop to maintain high production volumes throughout the year, irrespective of climatic conditions. The red paver block production industry in India has witnessed substantial growth due to the surge in infrastructure development and urbanization. Paver blocks, especially red ones, are widely used for landscaping, roads, parking areas, and pathways, driven by their aesthetic appeal and durability. India's paver block market is estimated to grow at a CAGR of 7 to 9% from 2023 to 2028. The annual demand for paver blocks, including red ones, exceeds 5 million square meters, with Tier 2 and Tier 3 cities contributing significantly. The industry is dominated by small and medium enterprises, accounting for over 80% of the production, leveraging semi-automatic and manual production units. A typical red paver block manufacturing unit can produce 1,000 to 3,000 blocks per day, depending on the machine type and labor efficiency. Large-scale manufacturers use fully automated vibro-compaction and hydraulic machines, offering production capacities of up to 10,000 blocks per day. Key inputs for production include cement, 25–30%, sand, 40–50%, aggregates, 20–30%, and iron oxide for pigmentation. With red being the most popular color. The cost of production for a standard red paver block ranges between 12 cents and 24 cents, while the retail price is approximately 30 cents to 60 cents, providing attractive margins for manufacturers. The production process of roof tiles from recycled plastic involves several key stages, utilizing specialized machinery designed for efficient manufacturing. Recycled plastic material is first fed into the extruder, where it is melted and mixed with sand to form a homogeneous blend. After molding, the tiles are transferred to the press machine for compaction, ensuring strength and durability. Once pressed, the tiles are passed through the calibrator cooler, which cools and finalizes their shape and dimensions. This blend is then directed into molds, shaped according to specific country standards or customer requirements. The molding phase is crucial, as it defines the tile's dimensions and surface finish. The system produces up to 60 tiles per hour, making it a cost-effective and eco-friendly solution. The installation required for this process includes a specially designed extruder, 2 molds, one for tiles and another for covers, a press machine, and a calibrator cooler for finished products. The equipment operates with an installed power of 20 kilowatts and requires a working area of approximately 20 square meters, excluding warehouse space. The Keta Schermaker Autoclaved Aerated Concrete (AAC) production line is a fully automated process designed for high efficiency and precision in manufacturing AAC products. The primary raw materials used in this process are calcium-containing materials, calcium oxide, and silica-containing materials, silicon oxide. These materials are first processed in a ball grinding mill to achieve ultrafine quality, ensuring they meet stringent technological requirements. Once ground, the materials are transferred to a mixing tank equipped with an internal stirring device that maintains uniform density throughout the contents. The pouring mixer can handle a wide range of densities, from grade 0.3 to 0.7, ensuring flexibility in product types. Following the mixing and pouring stages, the pre-curing process begins. An independent mold position detection system monitors the pre-curing room, where the central control system ensures accurate dispatching of the cake ready for cutting. Once pre-cured, the mold is transferred to a demolding machine featuring a hydraulic self-locking hook and chain lifting system for precise and stable operations. The cutting process involves multiple stages to achieve high precision. The surface cutting machine performs rough and finished cuts on both sides of the mold. A horizontal cutting machine minimizes settlement cracks during thin plate cutting, with a minimum plate thickness of 50 millimeters. Additionally, a vertical cutting machine uses a swing frame cutting mode with a high-precision guideway slide, ensuring a lateral error of less than 0.5 millimeters. Semi-finished products are clamped and transported to a tilting table for layer removal based on specified thickness requirements. After marshalling, the products undergo autoclaving, followed by automatic unloading via ferry car. The stacked products are separated by a dedicated system to prevent adhesion before entering the double-chain packing line. This system combines two 600 mm wide blocks into a 1200 mm width to match the tray size. Finally, the packed AAC products are transported to the storage yard by forklift, completing the highly automated production process. Handmade tile production is an intricate and meticulous process, combining artistry with technical skill. In the Cotswolds, Tiles of Stowe exemplifies this craftsmanship, creating unique tiles that reflect traditional methods. The process begins with sculpting, where the original designs are carved in clay. These carvings serve as the foundation for plaster molds, which are used to replicate the tiles. Clay is carefully pressed into these molds, ensuring that every detail of the design is captured. This stage requires precision, as the quality of the mold determines the clarity and definition of the final product. Once molded, the tiles are set aside to dry, a process that typically takes about a week. Drying time can vary depending on ambient weather conditions and the operation of nearby kilns. During this period, the tiles undergo gradual evaporation of moisture, preventing cracks and warping. After drying, the tiles are fettled to remove any imperfections or rough edges, ensuring a smooth surface. The fettled tiles are then subjected to a biscuit firing at approximately 1020 degrees Celsius. This initial firing hardens the tiles, making them durable and ready for glazing. The biscuit-fired tiles are dipped in specially formulated glazes, which provide both aesthetic appeal and a protective layer. Each glaze is carefully chosen to enhance the design, with the potential for vibrant colors, subtle finishes, or intricate patterns. Once glazed, the tiles are re-fired in the kiln, where the glaze melts and bonds to the surface, achieving the final finish. This process requires patience and dedication, as each stage demands attention to detail and precision. The end result is a collection of handmade tiles that carry a distinct character, whether intended for local churches or other projects. Each tile embodies a blend of artistry and tradition, ensuring its place as a timeless and functional piece of art. Hope Cement Works, the largest cement manufacturing site in the UK, produces up to 1.5 million tons of cement annually. The production process begins at two quarries where limestone and shale, key ingredients for cement, are extracted. The limestone quarry spans 1.5 kilometers in length, 600 meters in width, and 170 meters in depth, with 13 active working faces. Formed 330 million years ago, the rock is accessed through controlled blasting, producing around 20,000 tons of material per blast. The extracted rock is crushed in 3 stages, reducing it from 1 meter in diameter to stones smaller than 20 millimeters. Once crushed, the limestone and shale are transported to mills where 205 tons of steel balls grind the materials into fine powder. Pulverized fly ash, PFA, a byproduct from coal-fired power stations, is also used as a partial replacement for shale. The resulting raw meal is transferred to a blending silo and then sent to a preheater tower where it is heated from 80 degrees Celsius to 830 degrees Celsius. The preheated material is fed into one of 2 massive kilns, each 70 meters long and 4.8 meters in diameter, lined with 70,000 heat-resistant bricks. The kilns operate at temperatures exceeding 1,500 degrees Celsius, enabling the chemical transformation of the raw material into cement clinker. Fuel for the kilns includes coal and sustainable alternatives like scrap tires and processed waste, with 35% of the fuel sourced from sustainable materials. Emissions are closely monitored and controlled to meet stringent environmental standards. Once formed, the clinker is rapidly cooled from 1,400 degrees Celsius to below 150 degrees Celsius and stored before being finely ground in cement mills. Additives like gypsum are introduced to control the setting time of the final product. Approximately 1 million tons of cement are transported annually by rail, reducing the environmental impact by eliminating over 6,000 lorry journeys. Additionally, 55 lorry loads leave the site daily, delivering cement to depots across the UK. Amrapali Precast Factory, Asia's largest and most advanced precast unit, operates over a sprawling 25-acre facility in Greater Noida. The factory employs state-of-the-art technology for mass housing projects, ensuring high-quality, cost-effective, and time-efficient construction. The production process involves multiple stages, including the manufacture of hollow core slabs, wall panels, staircases, and various structural components. Hollow core slab production. The process begins with cleaning the casting bed, followed by placing and stressing the strands for pre-tensioning concrete. High-strength dry mix concrete is prepared in a fully automated batching plant, ensuring uninterrupted supply. Concrete is transported using an automated flying bucket system, unloaded into the extrusion machine hopper, and cast onto the strands. Once casting is complete, the slabs undergo quality testing, including the testing of 150 mm cube molds. After curing, the slabs are marked, cut, and transported to the stockyard for stacking and further curing. Wall panel and other element production. Wall panel production starts with cleaning and oiling the tilting tables. Magnetic molds with shutters are fixed, and reinforcement mesh, lifting inserts, and utility provisions are placed. Concrete is then poured and compacted using built-in vibrators, followed by surface finishing with power floaters. After achieving the required strength, panels are demolded, transported vertically on specially designed A-frames, and stacked in the stockyard for curing. Staircase and structural component production. The factory also produces staircases, beams, balconies, and cupboards. Similar steps of cleaning, oiling, molding, concrete pouring, and surface finishing are followed. The components are cured, transported, and stacked for dispatch. Erection at project sites. At the project site, precast units are lifted using specialized clamps and placed at designated positions with the help of skilled workers. A unique identification number on each component ensures accurate placement. Components are joined using grouting techniques to provide structural rigidity. Precast technology significantly enhances the speed of construction, reduces material wastage, and ensures better environmental safety. Compared to conventional methods, this approach cuts project timelines by over 60%, delivering durable, maintenance-free, and earthquake-resistant structures. For the Jama El Jazer Mosque in Algiers, Europols utilized BHS Sontofen's advanced twin-shaft batch mixers to create premium white, high-strength spun concrete. This included precise aggregate dosing, binder and water mixing following a proprietary recipe, and efficient discharge to transportation units. The reinforced drive of 65 kilowatts and counter-rotating shafts ensured uniform mixing. Column molds equipped with rebar were filled, centrifuged, and processed to form 34-meter-long, 34-ton columns. Traditional brick production in Nepal relies on manual processes and primitive kilns, such as the bull's trench kiln. This method requires significant labor and consumes high amounts of coal, about 25 to 30 kilograms of coal per 1,000 bricks, leading to higher pollution and lower efficiency. Daily output typically ranges from 10,000 to 15,000 bricks, with inconsistent quality due to manual shaping and firing. In contrast, modern machinery-based production uses advanced kilns like the vertical shaft brick kiln and fully automated machines. These methods reduce coal consumption to 15 to 20 kilograms per 1,000 bricks, lower emissions by 50%, and increase daily production to 20,000 to 40,000 bricks. Additionally, modern techniques ensure uniform brick quality, improved strength, and lower labor costs by 30 to 40%. The automatic brick-making machine is a high-efficiency solution designed for large-scale brick production. This machine can produce up to 5,300 bricks per hour, significantly reducing labor requirements through its advanced automation features. The process begins with the box feeder, which ensures consistent feeding of raw materials into the system. The materials are then processed through a roller mill, where they are finely ground and homogenized. Next, the mixture moves to the extruder and mixer, equipped with a wear-resistant, high-chrome extruder auger. The de-airing extruder removes air bubbles, enhancing the brick quality. Once the mixture is formed, the brick cutter precisely cuts the extruded clay into uniform brick sizes. An automatic brick stacker efficiently stacks the bricks, optimizing the drying and firing process while minimizing manual handling. Manufactured with premium-grade materials, the machine ensures durability and long-term performance. The construction of Shefferland's Bridge involved a comprehensive approach, utilizing advanced precast concrete solutions to ensure efficiency and durability. Shea Murtaugh Precast, a leading manufacturer of precast products in the UK and Ireland, played a key role in this project. The process began with careful design, where bespoke precast elements were developed to meet the specific requirements of the bridge. These included beams, culverts, retaining walls, parapets, and copings. The company's expertise in managing every aspect of the project, design, production, and logistics, ensured smooth execution. Shea Murtaugh Precast's in-house logistics and transport teams efficiently delivered the precast components to the construction site, reducing on-site labor and enhancing the speed of construction. The production of tiles is a sophisticated and highly automated process. At Ceramic Industries, the largest manufacturer of tiles in southern Africa, both ceramic and porcelain tiles are crafted with precision to meet modern design demands. The process begins with the mining of raw materials, primarily clay and sand, from quarries. These materials are crushed and milled into fine particles, mixed with water, and combined with additives to create a uniform mixture suitable for tile production. For porcelain tiles, cement in the form of andesite is added to the mix to enhance its durability. Forming the tiles. In the vitro factory, porcelain tiles are shaped through extrusion. The mixture is pressed through a metal die, forming sheets that are cut into tiles. Ceramic tiles, produced at the neighboring Pegasus factory, are formed differently. The mixture is pressed into tile shapes using specialized molds. Both factories process immense quantities of raw materials, up to 900 tons per day, and produce tiles as large as 600 millimeters square. Drying and printing. The tiles undergo a drying process to reduce moisture, enhancing their strength. A primer coating is then sprayed onto the tiles to prepare them for pattern application. Designs are added using either screen printing or advanced inkjet printing technology, enabling intricate and customizable patterns. A protective glaze is applied, which becomes transparent after firing. Firing and finishing. Tiles are fired in a kiln, where temperatures reach 1185 degrees Celsius. This step hardens the clay and ensures durability. Gradual cooling prevents warping or cracking due to thermal shock. After firing, each tile is inspected for quality, graded, and sorted by robotic machinery. The factories operate 24/7, producing up to 500,000 tiles daily for both domestic and international markets. The production process for playground flooring involves several key stages to ensure safety, durability, and design flexibility. First, the substrate preparation is essential. A smooth, clean surface, either asphalt or concrete, must be prepped to ensure proper adhesion of the flooring materials. For asphalt, a slight slope of 0.7 to 1% is applied to facilitate water drainage, while for concrete, a power-troweled surface is preferred to eliminate cracks and ensure minimal moisture content. Once the substrate is ready, the application of PU Primer 870 is the first step. This polyurethane primer is applied to the surface in 2 layers, ensuring strong adhesion of the subsequent materials. The primer must create a slightly tacky surface, ideal for the rubber and binder mixture to bond effectively. The next step is the preparation of the rubber mixture. This involves combining PU Binder 1118 with recycled rubber granules, 1-3 mm, for the first layer, known as SafePull, and with EPDM granules, 1-3 mm or 1 to 4 mm, for the second layer, SafePull Multicolor. The materials are mixed using a low-speed mixer, ensuring an even distribution of granules and binder. The mixture is spread onto the prepared surface using tools like rakes, straight edges, and flat trowels. The layer is then compacted with a roller to achieve the desired thickness and smoothness. After curing, the final UV-resistant topcoat, Polysport XP 1069, is applied to protect the flooring from UV damage, ensuring long-term performance and vibrant colors. The entire process results in a safe, durable, and aesthetically pleasing playground surface.